I shall start the official recording and say hello, happy garbage day. Thank you all for being willing to meet with me on Zoom here. I'm not doing too badly, but I'm not 100, so you don't want me to make you sick. Over spring break, I stayed at the Great Wolf Lodge in Kansas City for 2 nights. So it's kind of amazing that I didn't come back with diphtheria or tuberculosis or some other like Oregon Trail level disease from all of the children running around there. It was an entertaining place, I will say, but if you're looking to go there for a good night's sleep, that is not going to happen. I'll just tell you that right now. The children are running and screaming and slamming doors at all hours of the day and night. And they have a excellent arcade that is open 24 hours. So, just in case your 5-year-old wakes up at 3 a.m., that's where you'll find them. But anywho, so hopefully everyone had a relaxing and/or fun break. We're ready to do the second half of the semester. Ready to fake it? Anyone else going to just fake it with me? We're just going to fake our way through the next 8 weeks and get through it. Yeah, that's my plan right now. All right, do I need to put the formative assessment up on the screen share to remind us, or do you want to look on your own devices? Any thoughts? I know it's sort of weird when you can't see each other, so. No one cares? Okay, well, then we'll just do the screen share, and then you don't have to worry about missing out. So, okay. All right, recording is going, screen share is going. We've got some questions to answer. I did go through and update grades this morning, so you should be able to see your current point totals. So first question then, point of intersection across the two classes at the moment. What's a logit and what's a probit? So more generally, what are these things examples of? What's the more general term that would be over these? What are they called? And you can talk or you can type, your choice.
Link
They would be functions.
Yes, link functions. I heard it almost in stereo here. So logits and probits. So let's go definition time. What's a logit?
The log of the odds of the probability of a 1.
I said it better myself. Yes, indeed. And then what's a probit?
It's an ogive transformation based on the normal distribution.
Yes. So I would go with I heard the phrase standardized logit. I would accept that. It's based on the normal distribution, as was said. You can think of it as a z-score. So it's the z-score that corresponds to that amount of probability as the area to the left under the standard normal distribution. And both of these things serve the same purpose, which is to make sure that the predicted probabilities of a 1 response do not go out of bounds. So a few folks mentioned things, I think, about transforming data. That's not the case. So the zeros and ones that we're going to be predicting as item responses are staying in the 0-1 form. We're not changing those. What changes is the conditional mean that's being predicted by the model, or E of y in stats terms. And that's not a distinction we typically make when we're talking about continuous outcomes, because we just talk about predicting y. But really we're predicting the expected value of y, which is the mean. So that's why we talk about logits and probits transforming the predicted probability of a 1 as the conditional mean that's being predicted for binary items, but not the original zeros and ones themselves. And the logit and probit aren't actually defined at 0 and 1 anyway. So they keep our predictions in bounds. That's the big picture for those. So any thoughts or questions on number 1? Go. Guess what? When we start talking about predicting ordinal responses, guess what we're going to use then? Guesses? It's the same thing we would do in ordinal regression. Okay, well, that's coming later, but it's still logit and probit is what I was going to say. It's just the cumulative version of that. So these concepts will still with us, for quite a while. Okay, IRT time then. So A and B parameters. Which one is discrimination? Have it? Yes, indeed. So which one is difficulty? It's the B, yes. And that is backwards from how you would think about it in like a linear equation like algebra, like mx plus b. B is the constant in that case. B is not the same thing here. A is the slope. B is difficulty, which is not the same thing as an intercept. So in these models, which is included if you only have a one parameter or Roche model? Different A's per item or different B's? In a Roche model. Oh, got some of both. It is B. Yeah, it goes in the opposite order. So the one parameter model starts with a different B per item, and then the two parameter model adds a different A per item. So if you're used to that terminology, one parameter being a synonym for Roche with a different method of identification. So let's start with B. What does B tell us as an index of difficulty? It has a very specific definition, such as in a two parameter model.
In a two-parameter model, B is the theta required to have a 0.5 probability of getting the item correct.
Yes, exactly right. So in a two parameter model, it corresponds to the point on the trait, or theta, where the probability of a 1 endorsing the item or getting it correct is 0.5. It'll be shifted upward by the C parameter in a three parameter model, but it's the same idea. It tells you for what kind of trait level that item is going to be maximally useful or maximally informative. So B tells you in colloquial terms who the item is for, what kind of person with respect to their latent trait. So then A is the slope at that B location specifically. It's the maximum slope on the nonlinear curve relating theta to a predicted item probability. So B in this case is difficulty. It's indexed in the correct direction, and that higher values correspond to items that are more difficult or have a lower likelihood of being correct or endorsed. And A then controls how informative that item is at that location. So both of those things are necessary to talk about how useful an item is, not only for whom it's useful, which is what B tells us, but then at that point, how useful is it, which is what A tells us. And sometimes you can have A's that are relatively low if they're paired with item difficulty levels that are extreme, because it's harder to find a steep relationship if you have relatively few cases, at those ending points. We started talking about intercepts and thresholds last time. That will probably show up on the next formative assessment, depending on when that falls. But we'll talk more about those today as well. But I don't want to introduce that additional terminology just yet. So any questions or things you want to hear again for that? Number 2? Okay. Question 3 then, conjoint scaling. So this one I had a wide variety of responses to. Conjoint scaling, almost everyone mentioned some idea that the items and people are on the same trait. But then more specifically, if I told you that someone had a trait estimate of 2, what does that tell me about their predicted responses to items either below a difficulty level of 2, at 2, or above 2? If we think of it that way.
They are more likely than not to get items of a difficulty lower than 2 correct, and less likely to get items above a difficulty of 2 correct.
Yes, so somebody who has a trait level of 2 then has a 50% chance of answering an item of comparable difficulty, and difficulty of B equals 2, correct. And so then you would expect a greater likelihood of items that are less difficult, greater likelihood of items that are less difficult, a lower likelihood of items that are more difficult. And 2 is not necessarily meaningful in any absolute sense. So if we use a method of model identification in which theta has a mean of 0 and a standard deviation of 1, which is very common, then 2 would be somebody who has a relatively high theta level, 2 standard deviations above the mean. But that isn't necessarily the case. The idea of conjoint scaling is that the trait value is directly informative as to what kind of items that person is likely to endorse or get correct, and which ones they won't and which ones they definitely will, or most likely will, I shouldn't say definitely. So that's the idea, is that these numbers don't have any absolute meaning, have meaning relative to the combined scale of the two. So that was the idea that I wanted to tie this idea of what B means into what theta means. They kind of are the same idea, but B is an item thing and theta is a person thing. So any questions or comments on that one? All right, and last one. Factor score reliability. How is it evaluated differently in IRT than in CFA? I don't need the formulas, just the big picture. So let me phrase this as a series of yes or no questions instead, because I think that will go better. In a CFA model for continuous responses, is reliability constant across the trait or not constant? Everyone says constant. That is correct. So we compute a number that is supposed to be the reliability no matter where your factor level is, no matter where your trait level is. And that is a consequence of the fact that the model specifies a linear effect of theta in predicting the item responses. And because a linear slope goes on forever, there's no point at which that item becomes less discriminating. So the linear slope implies a constant item information function across the trait. And if you literally add those up, you can come up with an index of test information, which you can convert into reliability. People don't typically talk about it that way in CFA, but if you think of it from that perspective, then it becomes easier to see how the opposite happens in IRT. So in IRT, do we have constant reliability or non-constant? Non-constant. And why is that? Why is it? It's not linear. Those are both correct, but let's put some nouns in there. What's not linear? Different items have different information at different levels of the trait, yet also true. And that is also a consequence of something not being linear. Items have different discriminations, which means different standard errors. I would say that standard error of theta is tied to both discrimination and difficulty. Difficulty is not the same across theta. Difficulty is supposed to be constant as an item parameter. Discrimination, yes, I'll give you that one. Yes, nonlinear is the key idea, is the slope relating theta as a predictor to how it creates an expected probability of an item response. That slope is nonlinear. So that implies that for every item, there's some point at which the slope is at a maximum. It's going to die off as it goes closer to 0 and closer to 1. So then reliability is a function of two things. How many items you have at that corresponding difficulty level dictates how reliable your scale will be at that point on theta, but then also how discriminating are those items at that point. So if you have 3 items in one scale at theta of 0, let's say, and 3 items from a different scale, they could have different amounts of information because of their different A parameters, but the amount of information at theta of 0 is going to be dictated by the number of items with a difficulty level of 0, and the same would be true. So yes, it's the nonlinear function that relates theta to the predicted item probability. That's why we end up with non-constant information per item, which you can sum across items to come up with an overall information curve. So that's the idea of, you can't just say whether a measure has sufficient reliability, but it's for whom. Are you measuring people high, medium, and low? If that's your goal, you would want to have maximum reliability that's a relatively flat function, whereas if you're more concerned about one end of the distribution than the other, then you'd want to maximize reliability on that end where you're concerned. Excuse me. All right, So that is, I think, the last question. Yeah. So any of that you want to hear more about or talk about more? We're good with that? Okay. Let me ask how homework 3 is going. Remember that? Yeah, homework 3 is the next item up for bids in this class. See classical test theory and CFA on your own data. Okay, who's talking? Go ahead.
Lisa, if
Yeah.
our item responses in our data for homework 3 are like kind of all over the place, not really normally distributed at all in some cases, but are in other cases, is that still okay to use for this homework, or
Yes.
should I abandon ship? Okay.
So can you tell me, like, when you mean not normal, what that looks like in your case?
Yeah, sure thing. So, uh, I'm doing an analysis of GORT scores, and so some of the higher items have most kids are at score 0, so it's like 0 inflated, I guess, for some items, and there's just not much variation.
Okay, is each item scored 0, 1?
No, it's 0 through 10. So,
okay.
Yeah.
Okay, yes, absolutely. Just pretend all of it's normal, because that's what people would normally do. Pun intended.
Okay, great.
So the objective here is for you to practice CFA with the understanding that for, I think, all of you, that's probably not the right model. But it is the most common, and it is a logical jumping off point to get started. And then for homework 5, then you would ideally use the same data and fit the proper model, a binary model, an ordinal model, or whatever you need in your particular case, so that you can see how your conclusions about dimensionality and reliability and such would change under a different model. So yes, you all have permission for homework 3 to pretend your items have a normal distribution, even if that is not remotely the case. That's part of the learning. Okay. If you get stuck, please let me and the TAs help you. We are happy to weigh in on badly fitting models. Sometimes it can be badly fitting just because of an error. So before you come to any horrible conclusions about your items are terrible, double check that M+ is reading your data correctly. Check with the descriptive statistics at the front that they match your items and that you didn't miss a variable name, for instance, and have it reread the file incorrectly. Also, when you're fitting factor models, make sure that if you are fixing the factor variance to 1, that you've estimated all of the item loadings, and that will most likely be a problem if you forget your star after the first one, because it will fix the loading to 1, and if you have the factor variance fixed to 1 too, that's a double constraint, in which you would then be saying that your item is perfectly related to the trait, and that is probably not going to be the case. So there may be just some easy things that can go wrong that would cause your model fit to look completely terrible. If you've checked those things and it still is like, I have no idea how to fix this, let us help. We're happy to weigh in. If you have bad items and you want to drop them and see what happens, that's fine with me too. I'm expecting that not all items will be equally useful, particularly for measures that are undergoing development as part of this process. For measures that are more established, such as the GORT or other things that people are selling commercially, I would probably not throw out bad items, so to speak, but anything is fair game when you're first undergoing scale development and evaluation. So, all right, I've got lecture 5B here up. Shall we jump back into that for a minute? We're not going to talk about estimation today, only like this much, okay? It's hard for me to talk about estimation when I'm firing on all cylinders, and that is not the case today, so we're going to make it work. I do want to talk about fit and the alternative. So we talked about this last time. Let's pick up on slide 25 here. So in IRT models, item response theory models, in predicting binary outcomes, if you're using full information maximum likelihood, what that term full information means is that you are using all of the original item responses to build the likelihood function per subject. So each of the responses is conditionally independent after you control for theta, and you can multiply all of those predicted probabilities and come up with a likelihood for each person. So in terms of what the right answer is, like what the saturated model is to come back to, what would be the highest possible likelihood for your data, that comes from the number of possible combinations of item response patterns. So this gets very big very quickly. So if you picture, for instance, 24 binary items, such as you will have in homework 5, and you fit a 1-parameter IRT model, so in that model, each item would get a different difficulty level, and that would be the only thing that you would have to estimate. The number of possible degrees of freedom is 2 to the power of 24 minus the number of loadings A discrimination parameters and B difficulty parameters minus 1. So you can see that becomes ridiculously large. So in practice, there is really no way that we can compare the predicted combination of cross tabulations of all possible response patterns to the one observed in the data. We don't have all the people to fill out all the cells, and it's probably not going to have, like every cell is not going to be full, like logically speaking, because these items have correlation to them. So in what we'll see an example in M+, if you fit full information maximum likelihood to these models, if you use that to estimate them, you're going to get no information about fit. And that doesn't mean it fits, it just means we don't have information about it. So practically speaking, what I will show you how to do is to use a different approach to estimation to evaluate fit. Because then we can get back to something that looks like a saturated model and all the regular indices of model fit instead. So there are newer measures of fit that I want you to be aware of. So here's a person who's been working on that, and these are the keywords that you would search for. These measures of fit look at the recovery of the IRT model in predicting the marginal probability, so like the number of zeros and ones for each item, as well as the bivariate, so the two-way tables of the data have 0 and 1, what did the model have for 0 and 1, and how well do they match. And so these statistics work with that two-way summary only, which is why they're limited information with respect to assessing fit, but the model parameters that you're using to generate those expected contingency tables are based on full information. So it's kind of like a weird hybrid in the sense that the model's being estimated one way, but fit is being checked in another way. These are the things that I would point you towards if you're interested in doing more with respect to model fit for full information stuff. So what we will do instead is based on a different strategy, which is to work with limited information. So the estimator that we'll use for this goes by a couple different names. It is known more generally as diagonally weighted least squares. In M+, it's known as WLSMV, and here's the long thing for this. Basically, the idea is that rather than trying to compute a Pearson correlation matrix and then get the model fitted to that, we're going to adjust it to be a different kind of correlation matrix that's more appropriate for binary or ordinal items. So what we're going to do then, talked about that last time, is under the line here on slide 30. So tetrachoric correlation is what it's called among binary items. Polychoric is what it's called for ordinal. And then you get the serial combinations of those if those correlations are paired with actually continuous items. So these matrices, these types of observed correlation matrices, what will happen is essentially the model, the program will compute a saturated version. So just compute the tetrachoric correlation matrix or polychoric for categorical. And then it will use that matrix to estimate the parameters. So we're starting with a summary and then fitting the model to the summary. And for CFA models, this would make no difference whether you computed a Pearson correlation matrix and estimated the model using that. The only difference would show up if you had missing data. Whereas for ordinal and binary outcomes, there will be a difference in terms of what you get back. So we have this idea as tetrachoric. I think I've talked about this maybe at the beginning of the semester, but it's probably been too long when you should go back over it. Probably, yeah. So the idea of tetrachoric is, what if we had access to the actual underlying continuous variable that gave rise to our binary outcomes? And if we could think of it in those terms, what would the correlation be? So you can kind of think of this as like this is the correlation among the logits or the probits, and probits in this case specifically, rather than just among the observed binary responses. So the idea is illustrated here with this scatter plot. So if we have an item 1 and item 2 here, and if I were in intro stat class and I tried to draw a scatter plot for what zero correlation would look like, it would look like a perfect circle, right? We would have like a big cloud of points, and that would mean roughly that all the points are like equally distributed across the sections of the cloud. Whereas a scatter plot that looks like this type of oval instead, would illustrate a positive correlation. So we don't have all the individual points on this pretend underlying continuous variable because we don't have that variable. We have the binary version. But what we do have is the crosstabs across the variables here. So based on the proportion of cases in each of these cells, if we plot that into this kind of space, we can try to estimate what correlation would be consistent with the amount of cases in each of these quadrants. Where if it were a perfect correlation, we would have only D and A. A perfect negative correlation would have only C and B, and then anything in the middle is somewhere across the two. Sorry. So polyquark is going to work the same way. That's what we will use for ordinal items, and there is a much more helpful website I found about it that I'm going to link here, and here's the picture they took from it. So it's just more than 2 cut points in here instead for polyquark. And you can see from this expected table, for instance, like how much of a difference it can make in terms of whether you're reporting Pearson correlations or tetraquark correlations. For instance, if I have a variable with a mean of 0.5 and a variable with a mean of 0.9, the maximum Pearson correlation these two can have is 0.33. So that's a lot lower than 1. And obviously your factor model would look quite different if this was the input rather than something that's a little bit less subject to range restriction. Okay, I think that's, okay, we can do enough with that for right now. How about we look at an example? It's been long enough, don't you think? It's only like 97 slides and we're finally getting to an example. But this is one of the things where I haven't figured out how to break it down more completely. Okay, so example 5, I announced that we had posted yesterday. The data for these examples are not included in the download folder because these are real. So these data come from the octogenarian twin study of aging that I did some analyses with, quite a bit of analyses actually, when I was a postdoc. And yes, these are twins, and yes, I am completely disregarding the nesting of persons in twin pairs. Properly speaking, this should have been a multi-level IRT model, but I don't teach that class. So everything that you've learned about multi-level and everything that you've learned about IRT at the same time is what you would need for this. You would have a between IRT model and a within IRT model. I'm ignoring that for present purposes, so just forgive me. So we are looking at 635 older adults. So in this study, I took the baseline observations. They are 80 to 100 years old. So this is a very select population. And they were asked about 7 basic activities of daily living. And in this version of the response format, they had 2 choices. Either they need help doing it or they do not need help doing it. So not needing help is the endorsed or correct response in this case. So let's just look very briefly at the proportions. So for instance, 64% of the sample says they can do housework and so forth. Just looking at these numbers right here, what's my most difficult item? In terms of just the proportion of people who said that they can do this or not do this, which item is most difficult? Did I say most difficult or least difficult? I think I changed my mind halfway through. Which one is easiest? I think that's where I started. We got number 5. Number 5 or number 4, I would say. 64% versus 65%. Yeah. Which one is those? Those are the most difficult in terms of these. Which one's the easiest? Yeah, number 7. So 94% of the sample can use the phone. And by the way, that's not this kind of phone, folks. These data were collected in the 80s. This is like a landline on the wall, pick it up and answer it with a cord kind of phone. So most of the effort in answering the phone would have been getting out of your chair to go get it. So in this case, the fact that this variable is nearly a constant is going to cause some potential estimation issues. It's very difficult to assess its relationship with other things. So down here, what I have is a comparison on the left-hand side of the tetracorrelation correlation matrix I estimated for these items. You can do this in M+, you can do this in Lavon, you can do this in pretty much every software package. I have examples for you in the example 5 folder for how to do all of this stuff in Lavon, as well as how to do all of this stuff in M+. For the sake of brevity, I'm covering just the M+ side within this handout because this is the point where the answers start to differ based across programs, and we can't use Lavon for homework 5 or homework 4, excuse me, and get the exact same answers as M+. I had learned that before. But either way, within these values came from M+. So we have the tetric correlations here, and these are pretty high. They're all like between, like the lowest one is 0.68 all the way up to what, 0.92-ish, 0.93-ish. And so this gives me good faith that I do have items that are measuring something in common, but they're not exactly all the same thing. Otherwise, these correlations would be very close to 1. In comparison, on the right-hand side here are the Pearson correlation estimates. And what do you notice about the right-hand side versus the left-hand side? Throwing softball questions as I sip my Mountain Dew. Pearson correlations are a lot lower. They're all lower, some by quite a bit. So for instance, 6 and 7, 0.38 versus 0.82. So your conclusions about how related these items are would be very different under each method of assessment. Down here, I have the standard errors for these correlations, and for Pearson, they're all pretty much about the same, about 0.02, 0.03. But note that they are not all the same with respect to the tetrachorix. And the ones in particular that are the highest are with item 7. So if we look at item 4 and item 7, that standard error is much higher than all of the other ones, and that's because it has an empty cell. So this little crosstabs at the bottom of the table here shows that there are no people who could not answer the phone and shop. Basically, if you could shop, you were guaranteed to be able to answer the phone. And that makes sense because shopping is a much more difficult item. So it makes sense that if you can shop, you would have been able to accomplish all of the easier items underneath it. So what the software will do in this case where you have an empty cell is add some arbitrary tiny number to that cell just to make the math go. Like it will put in, 0.01 or something like that. And that causes this correlation to be much more of a guess as to what it should be because we don't have a lot of information with which to estimate it. So in terms of where least squares estimation is going to go, it's going to pay attention to not just this correlation matrix, but also how precisely these correlations are estimated. And the ones that are estimated better, as indexed by these smaller standard errors, are going to be given more weight in the analysis process. So that's where the weighted least squares idea comes from, is that it's weighting by the degree of imprecision with each of these correlations. And it's going to penalize, or not say penalize, it will not pay attention to those that are as estimated poorly. It will favor the ones that are estimated well in terms of what's being recovered by the model. So this is the basis for limited information. What I wanted to show you first, though, is full information and the lack of fit that comes with it. So I have two different models here. Let me zoom into the left side for us. This is M+ code to estimate full information maximum likelihood IRT model for these binary data. So most of this will look familiar to you, but this is probably a good thing to review since you're going to be working on homework 3 using M+ or Lavon. If you want to do homework 3 in a different stats package like Stata, that's fine with me. It's your data, you can do whatever you like. I can help you in any of these packages. So first thing it wants to know is where your data are. I use CSV format so that it opens neatly in Excel, but you can also give it a .dat files. Free format, so we're putting in individual data. Names is every variable that is in the data set. So case is my ID variable, followed by 7 items, and D stands for dichotomous instrumental activities 1 through 7. So you can name your variables in a way that makes the typing easier. For instance, in this case, if you keep the suffix as the number, then you can abbreviate a list of variables like this and not have to type all of them out. Use variables then says I only want to use the 7 that are for these binary items and not the ID variable. So if you forget use variables, your model may fit very badly because it's going to put your ID variable in the model with it and just let it like float out there. So it will be trying to capture relationships between ID and the other variables that are probably not going to be there. So that can mess some things up. Here's the new one. Okay, ready? Remember when I told you like 2 weeks ago that you only had to add 1 line of code to be able to do this? Do you remember that? Here's the 1 line. Categorical. And here's the cool part, folks. It's categorical no matter if you have 2 categories, 3 categories, 4 categories. Some have 2, some have 4, some have 6. It figures out how many you have. You just tell it categorical. Now by this, it really means binary and ordinal because there is a separate command for nominal. So categorical is a bit misleading. It's binary and ordinal specifically. So all 7 items are going to be treated as categorical in this analysis. Tell it about any missing data codes that you have. Technically speaking, you are allowed to leave it as blanks in fixed format data or as dots in free format, but I've had bad results with that, and so I'm sort of superstitious. I usually use the missing data code. I fill in those missing values before I send the data over to M+, just to make sure that I have everything aligned. And then this command here for ID variable, this is useful if you plan on outputting predicted theta estimates, because then it will make sure that that ID variable is in the file so that you can merge them back into your original data. So I think there's other ways you can include extra variables as well, but this guarantees that at least that one will be there for merging purposes. Type equals general is what we're still using in terms of analysis. That's not going to change throughout this class. Here are some extra things that are different than before. So we're still using maximum likelihood estimation, but we're using the non-robust kind in this analysis. The reason is that robust is overkill. So the robust part is designed to correct fit statistics and standard errors for deviations of multivariate non-normality of the responses. In this case, though, we're not assuming normality. We're telling it that these responses are binary, so there's no assumption that we need to worry about. In general, though, MLR simplifies to ML if you have a scale factor of 1, so you can use MLR when in doubt and it will be fine, but I decided to simplify just for the purposes of this example. Link equals logit. Can you guess what that does? Exactly what it sounds like. And this is why I want you to know the term link function, by the way, is because that is what the option will be called in your software package. So look for the term link, and that will tell you what the options are in terms of logits, probits, and whatnot. So within full information maximum likelihood, you can choose logits or probits. I am choosing logits in this case because then we can talk about conversions to probability very easily. Okay, still with me? Still microphone still working and all that stuff? Good. All right. Convergence. So this has a story to it. When I first started using the homework system with M+, I realized that people were running the same models on different operating systems or different versions of Windows and getting slightly different answers. And I was like, what? And it has to do with the amount of precision that is being used within M+, which is a lower standard than what modern computers use, from what my husband tells me. So I wrote to the M+ people and I was like, how do I fix this? And this is what they told me: to tighten the convergence criterion. So for these models, this should make it so that the results are more comparable across different operating systems and even versions of the same operating system. And it has worked so far. So I'm adding this just to make sure that we all end up at the same place, really. Standardized output I am requesting as usual. Tech 10 is how we ask for local fit information, and I will tell you this is going to add a whole bunch to your output. What Tech 10 provides is the observed versus expected discrepancy with respect to the marginal probabilities of your item responses, as well as every possible 2x2 table. So you'd have every combination of 2x2 table across the 7 items in this case, and it will tell you which ones deviate from what is expected in terms of the observed data versus expected by the model. This is going to be a nightmare to sort through, so we're not going to do that. We're going to look at fit via limited information instead, where it's much more compact. If you want to save predicted thetas, this is how you would do that. So you would ask it to save F scores, which stands for factor scores, and then you tell it what file they go to. And it has to be, from what I understand, a free format text data file, so .dat, but you can name it whatever you want. And by default, it will put your item responses into the same file, and unfortunately for any that are missing, it puts a star there. Well, if you read these predicted thetas back into a data set, those columns with predicted stars are read as strings, because a star is a string. So instead of having it do a star, you can ask it to put a number in there, and that way the columns will stay numeric when they come back to you. So that's one thing I've discovered that makes life a little bit easier. Plots. So there's 3 different types of plots. I've asked for all of them. These are different options that are useful for IRT as well as for describing distributions of factor scores more generally. Okay, so that's all the specification stuff in terms of the data and the model type. Any questions on that thus far? Then here's all you need to estimate the model. So IADL is the name of my factor. That stands for Instrumental Activities of Daily Living, which is what the scale that I took this from. Do you remember what the keyword by means? M+ only has 3 keywords for models: by, on, and with. What's by? Like, how can I think of a mnemonic? What does by mean? Is? What I go through in my head is measured by. Like, if you put that in there, then the list that follows is this factor is measured by these things. Okay. So I have item 1 through 7 with a star. So that star then applies to all of the items. That means that I'm asking it to estimate all 7 loadings. Question, how we define the named factor? Yes, that's not a question, it's an answer, yes. Can you name your factor anything you want? Within reason, 2 exceptions. What are the 2 ways you can break M+ by naming your factor wrong? As long as it's less than 8 characters, that's correct. 8 or fewer is the rule. The other rule, I'm pretty sure, is that you can't have it start with a number. That is the rule for variable names as well. So it needs to start with a consonant. Consonant, is that the right word? I know it's not constant. Consonant, there we go. I swear I'm here. It's like the fog is settling in. I feel like I'm San Francisco right now. But we're going to do this. Yes, 8 characters and start with a letter. By the way, M+ is not case sensitive. When I code, I usually put keywords in capital letters and everything else in some combination of title case. You can write it however you'd like. Here is the new thing. You don't actually have to write this, by the way, but I'm putting it here so that you see it. I made a joke about this before, but it's not really a joke. Do you see this special symbol here? We normally call that a $sign in US dollars. And the joke is, which is not a joke, these are referring to the thresholds that M+ is going to estimate. And if you understand this stuff, someone will pay you so that they do not have to. I am living proof of that. So these are factor loadings. These are thresholds. Now I'm going to pause for a moment there, put a pin in that. Down here, what am I doing to my factor? What is the purpose of the highlighted code here? Standardizing it? Yes, I'll take that. There's more to it though. What happens if I forget this part? Making it show we measure all the factor loadings. Yes, making it so we can estimate all the factor loadings. If I forgot this part right here gives the factor mean a 0 value, and it fixes it to that. That's a default. This part right here fixes the factor variance to 1, and that is not a default. So if I forget that, then it will try to estimate the factor variance and all the loadings, which makes this model not identified or broken. So yes, we have to anchor it or identify it. We're giving the latent variable a scale. So we're giving it a scale of mean 0, variance 1, standardizing it, but we could pick other numbers too. So if I wanted it to have a mean of 150, for instance, and a standard deviation or variance, excuse me, of 10, I could do that. But 0, 1 is the most common thing. There we go. Okay, what's not here that we had in our CFA models as a parameter? Yeah, I think I can read your lips, so type it. Yeah, error variances, yeah. Why aren't they here anymore? Not parameters. So in Bernoulli distributions, which is what these binary items are going to follow conditionally for each one of them, there is only one parameter, the predicted mean. And the predicted mean times the 1 minus the mean is the variance. So variance is not estimated because it's not constant, and it's determined by the mean already, so it's not here. So if we were to estimate, try to make m plus estimate the error variances, it would throw an error and be like, I don't know what you're trying to ask for here. There's no variances in categorical data. So we do have to type that. We do have to type that. We do not have to refer to the thresholds, though. Those are estimated by default. Likewise, the factor mean is fixed to 0 by default. But I don't want you to have to memorize the defaults, which is why I write everything down. Okay, so definition time. Do you remember what a factor loading is? It's a slope, right? So that's the change in y for a 1 unit change in x. And in IRT models where theta has a variance of 1, A, discrimination, and loadings are the same thing. There's a direct one-to-one, they're exactly the same number. Thresholds are not the same thing as difficulties. So let me back up one further. What's an intercept? Do you remember that? From CFA models or any other stats class you've ever had in your life? What an intercept is? Predicted outcome when x is 0. So that would be the predicted outcome for the probability of a 1, is what an intercept would tell you. So do you remember what a threshold tells you instead? Threshold is the additive inverse. Times minus 1. Probability of a 0. Yeah. Thresholds tell you the predicted logit of the probability of a 0 instead of 1. And that's what m plus gives you, whether you like it or not. If I want to turn thresholds into intercepts, what do I do? Yeah, additive inverse, multiply by minus 1. That's because logits are symmetric. So if I tell you that the logit for a probability of a 1 is 2, that means the logit for the probability of a 0 instead has to be minus 2. So there's a direct transformation back and forth. So even though n plus gives me thresholds, which I hate, I can turn them into intercepts quite readily. The reason that people use thresholds is because they're in the same direction as difficulty parameters. They are scored such that higher means more difficult, meaning a higher chance of having a 0 instead of a 1. Okay. Let's look at this fit. So the next page on the left-hand side has the fit of this model, 2-parameter model. First question, 14 parameters. How did I get 14? Give you a hint, I have 7 items. Two times 7 for the win. Yeah, this is a 2-parameter model, meaning each item gets one kind of loading / discrimination, and the other gets some kind of location parameter, either a threshold or a difficulty. HO value, what's that tell me? Can I look at that number and know anything? It's negative 1,454. Does that mean anything? Not really. What it's telling me is the height of my data under my model. Remember, I am the hoe. But what is it normally paired with? In CFA models, what would follow next? One, yeah. H1 is the most perfect saturated model, the right answer. It's the maximum height the data can be under the multivariate normal distribution, where every item has a different mean variance and every pair of items has a different covariance. Well, we don't have an H1 here. The H1 would be the height under the perfect model, which we don't have access to. So it's not here. So we have no idea if this model fits well. We have AIC, BIC, and another version of that, which notice they go in the opposite direction. So they are the -2 version. So these are shorter is better instead of taller is better. And these also don't have any absolute meaning. They only have meaning relative to a comparison model. So then we get these things down here, which are chi-squares, which is trying to assess relative to the full 2 to the power of 7 way contingency table, how our model predicted combinations of each cell would correspond to the ones in the data. And the degrees of freedom for this, 113, here's where those come from. So 2 to the 7 is 128 possible response patterns, minus 7 loadings, minus 1 thresholds, minus 1 gives me 113. So that's where this comes from. These two p-values, if they disagree, you're not supposed to use them. And they clearly disagree, so we're not going to use them. So this doesn't tell us anything about fit. Not a thing. There's nothing really that we can use out of this. What we can do, though, is use these things to assess relative fit. So let's, for the sake of illustration, compare this 2PL to its cousin over here, the 1PL, where there is one thing different. Let's see if I can get them both on the screen at the same time. Almost. There we go. Now you can see them both. We'll play Where's Waldo, syntax style. What's the one thing that makes these models different? Left side versus right side. Loading in parentheses for the win. What is it doing? It's doing two things at the same time. One is that it's holding all of the loadings to be equal. So it's making a constraint. And more generally, it is a label. So we are telling it, hey, can you attach the word loading to every estimated loading in this model? And by attaching the same word, all 7, we are saying make them all the same. So the labeling part comes in handy if you want to make it do math on your parameters, which we will need to do for ordinal data to get the IRT versions. But this is a constraint in this case, saying that instead of having 7 loadings, I want 1. In other words, what research question am I asking by comparing these two models? What do I want to know? Do I want to know by doing a comparison of a model in which all the loadings are equal to one where they get to be unequal? Is discrimination constant? Yes. We want to know which one is better fitting? Yes. Another way to think about this is whether a Roche model is sufficient. Which one of these is a Roche model? Right or left? The one on the right where the loadings are equal, yeah. So if reviewer 2 ever says that you should have used a Roche model instead, here's your answer. It's an empirical question. How do I answer that question? Any guesses as to how we can ask whether or not a model with equal loadings fits differently than a model with unequal loadings? Does this sound familiar? Compare log likelihood. Yep, likelihood ratio test for the win. Same thing you did as before. Loadings are considered parameters in the model for the variance, for those of you who've heard the multi-level side of these things. So anything that's involving changing the model for the variance involves a likelihood ratio test, always. Because this is just regular maximum likelihood and not the robust version, we can just do a straight comparison. So the model with 14 parameters in which all the loadings are separate has this log likelihood. The model with 8 parameters in which the loadings are shared, so there's a difference of 6 because it's 1 versus 7 loadings, has this log likelihood. I did the log likelihood test for you, reported right down here. Here's the difference. So difference is significant, a chi-square of about 20, p-value less than 0.05. So what do I conclude? They fit differently, but that's not the end of the story. Which should I go with? Which one should I go with, given that they fit differently? Got answers for both right now? I would argue that if there's a significant difference in fit after making a constraint, that means the constraint hurt the model. So I would go with the model that has all loadings unequal, because that fits significantly better. The model with all loadings equal fits significantly worse. This, of course, being subject to the same concerns about power for detecting differences, in which case power is a function of people. I've got 635 people and only 7 items, so I feel pretty good about that. All right, so where we are headed is 3 different versions of the results from that model. Not just 2, but 3. We have unstandardized results, which are going to give you loadings and thresholds. We have the standardized version of that, in which the total variance of y is 3.29. So that's what they're using as a basis of standardization. And then over here on the right column, so this is all for the same model, we have the IRT parameterization of A's and B's, discriminations and difficulties. For binary items, M+ gives us all of these things. But I think that we'll have to wait for next time. Does that seem fair? Okay. Then I want to use 5 minutes of your time right now to send out a pre-message for a message I'm sending tomorrow. As we mentioned before break, both of my classes this semester are going to be involved in a research study looking at how personal characteristics of students and instructors influence course evaluations. So for research purposes only, I'm going to send you an email with an invitation to participate in a course evaluation right now for this class, only for research purposes. You'll do a whole nother one at the end of the semester like normal, but this one is just for this because it has additional demographic questions. So I don't know who participates. I encourage you all to participate. It should not take more than 5 minutes. It's just the same standard questions, and I don't think there's much qualitative feedback on this one. So watch out for that email tomorrow because I believe you will have until the end of this week to complete that if you choose to participate. And I believe I get a summary of my data at the end of it, but I don't know from whom. Obviously, everything's going to be anonymized, so don't worry about that. You can say what you'd like for now, and I hope that you'll take the time to do your end of the semester evaluation, the ones that actually do count, so to speak. So, sound good for that? All right, then you can keep working on homework 3. Let us know if we can help you with anything. I have office hours tomorrow, and everyone else has office hours as usual. So, I think we'll call it good for today. All right, thanks for being here, folks. I hope to see you in person on Thursday. We'll let you know.